There are many small electrical devices in everyday use. All have three things in common: a source of electrical energy, a path for the electric current, and a component that uses electricity to work. Connecting them together creates a circuit. Switching on causes an electric current and the component works. Electric current is a flow of electrons. Electrons are negatively charged, and so they travel away from the negative terminal and towards the positive terminal. This model helps explain what happens in a circuit. The escalator represents the source of electrical energy, like a battery. It gives the charges potential energy by lifting them to a higher level. The paddle wheel represents the electrical component, like a light bulb. As the charges pass the wheel, they turn it and fall to a lower level, losing potential energy. All the electrons return to the escalator, where they gain potential energy again. Current is the amount of charge passing a point in 1 second. It's measured with an ammeter. In our model, the current is the number of electrons passing the paddle wheel per second. Voltage is the amount of potential energy the electrons are carrying. In our model, voltage is represented by the height of the electrons. The voltage between 2 points in a circuit is measured by a voltmeter. Here, reading the lower scale, it's 12 volts across the bulb. There are different types of circuit. Bulbs can be connected together one after the other to form a continuous loop. This is called a series circuit. Old-fashioned festive lights like these were wired in series and connected directly to the mains. But not all circuits are series. Connect each component directly to the power supply and the result is called a parallel circuit. Here, there's more than one path for the current. Modern low-voltage halogen lamps are connected in parallel, powered from a transformer. In series, watch what happens to the brightness when more bulbs are added. What happens to the brightness if more bulbs are added in parallel? To understand why brightness varies in the series circuit, we need to consider the current. With one bulb, the current is 0.4 amps. Add another bulb and see what happens to the current. The current is halved. Adding a third bulb reduces the current further. Bulb brightness depends on current. As the current falls, the bulbs get dimmer. To investigate current in a parallel circuit, consider our circuit with one bulb. This time, the current leaving the supply is 1.5 amps. The current returning is also 1.5 amps. Watch the ammeters carefully as a second bulb is added. The total current has doubled to 3 amps. Because the bulbs are equally bright, each bulb is taking 1.5 amps. Adding a third bulb results in 3 times the current of a single bulb. The total current is 4.5 amps. Each bulb has its own path to take current directly from the supply. That's why bulbs in parallel are equally bright. Finally, let's consider voltage, first in a series circuit. The total voltage of the supply is split between the bulbs. The voltages across each component add up to equal the total voltage of the supply. What about voltage in parallel circuits? In parallel circuits, the voltage supplied by the battery is the same as the voltage across each component. You can think of each component as being directly connected to the battery. This is a simple circuit, a bulb connected to a power supply. An ammeter measures current. A voltmeter measures voltage. When the voltage is increased, the lamp gets brighter. There's more current. More energy is being transferred. This suggests that current and voltage are linked. To investigate the relationship between voltage and current, we've replaced the bulb with a length of fine wire. The voltage is increased by regular amounts, and the corresponding current is recorded. In general, as the voltage increases, so also does the current. But to analyse this trend more closely, we need to plot our data on a graph. Values of voltage V on the y-axis are plotted against values of the current I on the x-axis. The graph is a straight line, which means that voltage and current are directly proportional. If the voltage is doubled from 1 to 2 volts, the current is doubled from 0.2 to 0.4 amps. If the voltage is 3 times greater, the current is also 3 times greater. So V is proportional to I. If we call the gradient of the line R, this proportionality can be written as V equals Ri. Rearranging gives R equals V divided by I. Check out what happens to voltage and current when the wire is replaced with a resistor. Plot the resistor data on the same graph and you can see that it's also a straight line, but this time it's steeper. For the wire, the gradient R equals V divided by I. So 4 divided by 0.8 gives a gradient of 5. For the resistor, the gradient equals 5 divided by 0.34 equals 14.7. The value of the gradient is known as the resistance and is measured in ohms. So the resistance of the wire is 5 ohms, but for the resistor, much more, 14.7 ohms. Resistance is a measure of how difficult it is for electrons to flow through a material. Here's our model of a simple circuit. There's an escalator as a power supply and paddle wheel as circuit component. Now we change the component for another with more resistance. The bigger wheel is harder to turn, so it's more difficult for the electrons to flow. They move more slowly, so the current is reduced. If the graph of voltage against current is a straight line through the origin, the component is said to follow Ohm's law. Ohm's law states that at constant temperature, voltage and current are directly proportional. But not all components follow Ohm's law. Look what happens to the current through a bulb when voltage is varied. Here's the graph. It's not a straight line. As current increases, the graph gets steeper. The resistance of the bulb is increasing. This time, voltage and current are not proportional, so the bulb does not obey Ohm's law. It's called a non-ohmic component. Compare these two bulbs. The energy available from the power supply is the same, but one bulb emits more light than the other. It's all to do with resistance. Some light bulbs offer more resistance than others. We're going to investigate resistance using different wires, and we'll measure the resistance with an ohm meter. First, let's compare wires of different metals. This coil of nichrome wire has a resistance of 5 ohms. The second wire of tinned copper, the same thickness and the same length, has a much lower resistance of 0.2 ohms. So different metals have different resistances. Imagine you could see inside the metal wire. Think of a metal as a lattice of vibrating positive ions, surrounded by a sea of free electrons. Apply a voltage and some of these free electrons move through the metal. In a metal of low resistance, these electrons can move easily, so there's a high current. In a different metal, there may be fewer free electrons, so the current is lower. We can say the metal has a higher resistance. As electrons move, they collide with the metal ions. Energy is transferred and the metal gets hotter. This bulb has a filament made of tungsten. Increase the current and the filament gets so hot that it emits light as well as heat. Further increasing the current results in the filament melting, breaking the circuit. Resistance is also related to length. This is a 30 centimetre length of nichrome wire. Its resistance is 1.4 ohms. What will it be if the length is halved? If length increases, what happens to resistance? The longer the wire, the greater the resistance. This variable resistor is a long coil of wire. Sliding the handle changes the length of the wire included in the circuit. The bulb is brighter when there's less wire in the circuit, so there's less resistance. Now, does thickness also affect resistance? Adding an equal length of the same wire effectively doubles the thickness. The thicker the wire, the lower the resistance. Look at our model of a thin and a thick wire. The electrons move at the same speed through both, but there are more electrons moving in the thicker wire, so there's more current, less resistance. Finally, how is resistance affected by temperature? Let's see the effect of cooling this coil of wire in liquid nitrogen. As the temperature of the metal falls, so does the resistance. Compare the metal lattice of a warm wire at the top with that of a cooler wire below. The metal ions in the warm wire vibrate rapidly. Electrons cannot move easily, so resistance is high. In the cooler wire, the ions are vibrating less. Electron flow is easier, so resistance is lower. At very low temperatures in some materials known as superconductors, the ions hardly vibrate at all. Here's a superconductor about to be cooled in liquid nitrogen. At extremely low temperatures, this material has little or no resistance. Placing a magnet over the top creates a small current in the superconductor. As it cools further, this current increases and the magnet levitates. Can you work out why? The superconductor's current produces a magnetic field strong enough to repel the magnet. Causes an electric current and the component works. Electric current is a flow of electrons. Electrons are negatively charged and so they travel away from the negative terminal and towards the positive terminal. This model helps explain what happens in a circuit. The escalator represents the source of electrical energy, like a battery. It gives the charges potential energy by lifting them . There are many small electrical devices in everyday use. All have three things in common: a source of electrical energy, a path for the electric current, and a component that uses electricity to work. Connecting them together creates a circuit, switching on to a higher level. The paddle wheel represents the electrical component, like a light bulb. As the charges pass the wheel, they turn it and fall to a lower level, losing potential energy. All the electrons return to the escalator, where they gain potential energy again. Current is the amount of charge passing a point in 1 second. It's measured with an ammeter. In our model, the current is the number of electrons passing the paddle wheel per second. Voltage is the amount of potential energy the electrons are carrying. In our model, voltage is represented by the height of the electrons. The voltage between 2 points in a circuit is measured by a voltmeter.